Hello guys, welcome back to my channel Gamma Digamma. So just to recap, in the previous video I had an introductory sequence into linear algebra. So we discussed about what row operations are and the reason behind doing them to simplify a system of equations. Now after watching that video, and I urge you to watch that video, let's actually solve a system of linear equations. Let's put the RREF, the row echelon form, and row operations to solve linear equations. Let's get started. Okay, to just give you a quick recap, if we had say something like this, and I don't know, say to solve this, what we would do in a process that's called elimination is multiply the first equation by 2 and then subtract this new equation that we get that by multiplying, which will be 4x plus 10y equals 12, from this equation, the original unchanged equation below. And when we do that, we get 7y is equal to 2, and we can solve the equation. So this process was basically called row operations because we took all the coefficients of these x and y and put them in a matrix. And how, I mean, is there a limit until which we should keep doing row operations? Yes. That limit is until the matrix is in RREF form, row echelon form. And we discussed this and we did a few examples, and we talked about pivotal columns or pivots and non-pivots. Okay, so now we're going to use this exact strategy of elimination. I mean, all this comes under elimination to solve systems of linear equations. And when we talk about solutions to systems, the entire discussion is focused on two ideas: uniqueness of solutions and the existence of solutions. It's like whether the solution exists. If it does, then we basically talk about the uniqueness, and if it doesn't exist, what is the geometric interpretation, or like what intuition can we give. I mean, I'm going to give intuition behind everything, but specifically the in the cases where the solutions don't exist. Okay, fair enough. Let's move on. Let's start on a fresh page. Okay, so we have a system of equations like this in 3 variables, 3 equations. So what I'm going to do is I'm going to basically take these coefficients, write them in a matrix. So I have 3, 2, negative 1. That's the first equation. Negative 2, 2, 1, 1, 1, 1. Fair enough. Multiplied with this xyz variable vector and equals this 6, 3, 4 column vector. I mean, in general we can write this system as ax equals b, where b is this column vector, a is this matrix, and x is this column vector. Now I mean, we need to solve this. So for solving this, we need to consider an augmented matrix, which is a 3, negative 2, 1, 2, 2, 1, negative 1, 1, 1. then have sort of a dotted line, forget this guy, and then just write this as a column over here, 6 3 4. This will help us in solving the system of equations. Why? Because we only need to perform row operations on this entire augmented matrix and get pivots in these three columns before the dotted line. So this is sort of the pivot area. I mean, you may get pivots, you may not get pivots. You don't need to find pivots in this column because that's anyways the constant. These are constants, so it wouldn't help much finding pivots there in the system of equations. Okay, so time to do some row operations. So what I'm going to do is I want a 1 here, right? I mean, this is the first pivotal position, the top left corner. I'm going to move this row 3 1 on top. So I'm going to do a row 1 row 3 exchange, and that applies to this constant column also, with 1 negative 2 3 1 2 2 1 1 negative 1 4 3 6. Now column 2 is column 2 plus 2 times column 1 because we need to get rid of this negative 2. Column 3 is column 3 minus 3 times column 1 because we need zeros in that column. So we have 1 0 0 1 4 negative 1 1 3 negative 4 4 11 negative 6. Fair enough. Now moving on to the next column, we need a pivot here in place of 4, so we can do an exchange now with the negative 1 below. So can't do an exchange with the top row because we don't, otherwise this will like change the position of this pivot. So exchange 2 and 3, 1 0 0 1 negative 1 4 1 negative 1 3 4 negative 6 11. Now what I can do is multiply row 2 throughout by negative 1, so that will make this positive, positive and positive. Fine, we're done with the placing the pivot. Now making the entries zeros. Row 1 changes to row 1 minus row 2. Row 3 changes to row 3 minus 4 times row 2. That will give us 1 0 0 0 1 0 negative 3 4 negative 13 negative 2 6 negative 13. Okay, now we can divide row 3 throughout by negative 13. That'll give us a 1 basically. And now making everything else 0. So row 2 is just row 2 minus 4 times row 3. Row 1 is just row 1 plus 3 times row 3. That will indeed give us pivots in every other column, and we have our matrix in row reduced echelon form, RREF. Bam. Pivots in every column. I mean, this can't be better. because now if we just multiply this back, this is basically the identity. That's the best part. We write this again like we originally had. You can notice, you can multiply and you can notice that x is equal to 1, y is equal to 2, and z is equal to 1. See, we have precise solutions. There's just one solution. We're damn particular about it. I mean, it's pretty evident that if we have pivots in all the columns, solution exists and is unique. Now, there might be some cases where the solution is inconsistent, but I mean, whenever we have square matrices like this, there's a big chance of this happening. I mean, I think about it this way. We have 3 variables, we have 3 degrees of freedom. We have 3 degrees of freedom, and we have 3 constraint conditions that we need to satisfy. I mean, so there's like this is like the supply, and this is like the demand. So the supply is equal to demand, so it's like there's a high chance of stuff getting satisfied, and that's exactly what's happening here. Like, whatever we need, we have exactly the right number of tools to find it. But again, even if it's a square matrix, that doesn't guarantee whether the solution will exist or will be unique, if it exists. I mean, there might be systems where with square matrices having infinite solutions or inconsistent solutions. But I mean, this pivot in every column case is super reassuring. I mean, you can't get any better than this. Okay, let's move on to another case now. Okay, moving on to another system of equations. Well, in this case, we have 3 variables or 3 unknowns. So 3 degrees of freedom, basically, and 4 equations. Four constraints that we need to satisfy, 4 conditions or constraints that we need to satisfy. Fair enough. Again, let's create an augmented matrix. Now, before doing row operations on augmented matrix, I think I should have said this, spelled it out clearly, that when we were doing RREF or row reduction in the previous video, we didn't consider augmented matrix. Instead, we just considered A, or in this AX equals B, we just considered A. We just considered the coefficient of the variable matrix. We did not take B into account and form an augmented matrix. But here we have to do that because you're solving a system of equations. If we wanted to simplify a matrix or check whether any 2 columns are dependent or independent of each other, I'm gonna, these are specific terms: independent, linear independence, dependence. All these are important terms. I'm going to probably make a video on this later. But we need to consider this augmented system now. That's why we need this dotted partition to differentiate between the coefficients and the constants. But every row operation won't care whether it's from this coefficient part or whether it's from the constant part. Row reduction applies to that entire row, but the part before the dotted is the pivot area, not the part after the dotted. That's the only difference. Fine, we have a 1, great. Row 2 changes to row 2 minus row 1. Row 3 changes to row 3 plus row 1. Row 4 changes to row 4 plus 3 times row 1. We have 1 and 3 zeros. Here we have 2, 1, 2, 6, 0, 3, negative 1, 0, 0, negative 4, 2, 3, fine. Moving on to the next column, and look, we have already a pivot here, so we just need to get rid of these other entries. So row 1 changes to row 1 minus 2 times row 2. Same thing with row 3 too. Row 4 is row 4 minus 6 times row 2, giving us 1, 3 zeros, 0, 1, 0, 0, and negative 6, 3, negative 7, negative 18, and 8, negative 4, 10, 27. Now we need a pivot over here in the third row in place of negative 7. So I don't divide row 3 by negative 7 throughout. I'll give us 1, 0, 0, 0, 0, 1, 0, 0, negative 6, 3, 1, negative 18, 8, negative 4, 10 over negative 7, negative 10 over 7, and 27. And now just make everything else 0. So row 1 changes to row 1 plus 6 times row 3. Row 2 changes to row 2 minus 3 times row 3. Row 4 changes to row 4 plus 18 times row 3. And it's going to be a little messy. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and we have negative 4 by 7, 2 by 7, negative 10 by 7, 9 by 7. And if we basically plug this back into this original equation, ax equals b, we get ax is negative 4 by 7, y is 2 by 7, z is negative 10 by 7. Fine, I mean you can say we're done here, but the issue is the last column will be 0x plus 0y plus 0z equals 9 by 7, which basically means that 0 is equal to 9 by 7. And this is a contradiction. And whenever you have contradictions like these, despite getting values for x, y, and z, you can say that the solution is inconsistent. So practically doesn't exist. And I mean, stuff like this happens when if you have, say, one equation and others which are basically intersecting, but like any other equation is parallel or just aloof from all of them. I mean, this equation can basically say x plus y is 3. This equation can basically, I don't know, just be like x plus y equals 9 or something. I mean they aren't perfectly parallel, but if you have two parallel lines like this, then they're never going to intersect anyway. There's never going to be a solution for them. Here it's not that evident what things are parallel, what things are not parallel, but it's just inconsistent. It's because I think about it this way. We have 3 variables, we have 3 degrees of freedoms, and we have 4 constraints. So we basically have more conditions to satisfy and less data or degrees of freedom to satisfy them with. So there's like some sort of shortage. That's the way I think about it, because if you're gonna do something like this, and if you still want a solution to exist, a unique solution to exist, this last row should have just been a row of zeros. We should not have had a 9 by 7 here like we did if we still wanted a unique solution. So in cases like this where the rows are more than columns, so the R is greater than C case that we discussed in the previous videos, for a unique solution, after row reduction, the last rows, in this case it was 1 row, but we can have many, should be 0 completely. I mean, in this case 1 row, because the difference between rows and columns was 1. R minus C was 1. That's the number of rows of zeros at the bottom that we need in general. Otherwise we're going to suffer inconsistency in the solution. Okay, let's look at another example. Okay, looking at this system of equations, well, it looks like we have 5 unknowns and 4 equations. So we have more degrees of freedom. Then we have conditions. So if we write this in an augmented matrix system, 2 1 1 negative 1 4 2 2 negative 2 1 0 actually 1 1 5 2 3 negative 1 6 2 4 1 2 1 2 1. If we write this in an augmented matrix system, you can see, ignoring this constant, this column of constants on the other side of the dotted line, we see that the columns are greater than the rows in this case. So if you remember, it's that system. And let's see what's particularly fascinating about this. Let's first, row reduce this to RREF completely. Exchange row 1, row 2. So we have 1 2 1 negative 1 2 4 2 negative 2 0 1 1 1, 2 5 3 negative 1, 2 6 4 1, 1 2 2 1. Now what I'm gonna do is again make everything go to 0. So row 2 changes to row 2 minus 2 times row 1, row 3 changes to row 3 minus row 1, row 4 changes to row 4 plus row 1, and we have 1 and 3 zeros, 2 and 3 zeros, 0 and 3 ones, 2 1 1 1, 2 2 2 3, 1 0 1 2. Now the issue is in the next column we have zeros at the pivotal position and zeros below the pivotal position, so we just need to skip this column, move on to the next one, and we have a pivot here. So just get rid of these bottom ones. Row 3 changes to row 3 minus row 2, row 4 changes to row 4 minus row 2, 1 3 zeros, 2 3 zeros, 0 1 0 0, 2 1 0 0, 2 2 0 1, 1 0 0 1. And now even in the next column there's no pivot, like there's no non-zero number at the pivotal position or below it anywhere, so just skip that and move on to the last column, and we already have a pivot there. And we just need to, I believe, move it up because the third row is the pivotal position right now. So we just need to exchange rows 3 and 4, 1 3 zeros, 2 3 zeros, 0 1 0 0, 2 1 0 0, 2 2 1 0, 1 0 1 0, and then basically get rid of the 2's that we have here. So I need to change row 1 to row 1 minus 2 times row 3, row 2 to row 2 minus 2 times row 3, with 1 3 zeros, 2 3 zeros, 0 1 2 zeros, 2 1 0 0, 2 2 1 0, but we have a 0 0 now because we got rid of them. And over here we have -1, -2 1 and 0, putting it back into our original AX equals B system. Let's just circle the pivots and the pivotal columns. So 3 pivots, 2 non-pivotal, or basically free columns. Fair enough. Now let's basically write the system of equation. If we multiply this by x1, x2, x3, x4 and x5, we just basically get this first guy, right? -1, -2 1 0. So we multiply this, write them as separate equations again. x1 plus 2x2 plus 2x4 is equal to -1 x3 plus x4 is equal to -2, x5 is 1, and luckily 0 is equal to 0. So it is pretty consistent. It seems pretty there's no contradiction until now. Okay. Now the basic idea about free variables, free columns, is that all the pivotal variables, let's call them pivotal variables, can be expressed in terms of the free variables. The way I think about it, pivotal P for passive. The pivotal variables are the passive ones, while the free variables are basically the active ones. And what do I mean by free variables, pivotal variables? Well, look at the pivotal columns. First column is pivotal, third column is pivotal, fifth column is pivotal. So that means x1, x3 and x5 are pivotal variables. In the meantime, x2 and x4 are the free active variables. So if we can write all these other guys in terms of x2 and x4 and a bunch of other constants, then that's the way to go. I mean, it's pretty clear with these bunch of equations that we can isolate x1. So x1 isolated is just -1 plus 2x2 plus 2x4. x3 is -2 plus x4. x5 is just +1, and I'm going to let x2 and x4 be any real numbers. I mean, again, this could be a part of real complex numbers, but again, that depends on the domain. Let's stick with real numbers for now. So the entire solution for this system, values of x1, x2, x3, x4 and x5 are as follows. -1 0, -2 0 1 plus x2 times -2 1 0 0 0 plus x4 times -2 0 -1 1 0. That's the entire solution. I for the sake of notation, I can call this x2 prime, x4 prime, because these are basically just scalar numbers, real numbers, any real numbers. And this is the general solution for this system. I mean, it's just so general that if you choose any x2 and x4 which are independent of each other, just any random numbers like square root 2 over here and pi instead of x4, it's still going to satisfy this system. That's why this system has infinitely many solutions. Just choose x2, x4, you get the value. I mean, if you remember, I had said that whenever we have columns greater than the rows, we're always going to have some free variables, some non-pivotal columns. And whenever you have a non-pivotal columns, at least one non-pivotal column, there is a chance of it being infinite solutions, or if there is some contradiction, then it can be inconsistent too. So we just need to check for stuff like this, like 0 equals 0, like this last row for example 2, because this can basically turn the tables of the game. And I mean, this form that I've written is of the form variables x is equal to particular solution p plus a linear combination of the vectors of the null space. I'm going to talk about vector spaces in the next video, and that's when I'm going to basically go in a lot more detail with column spaces and solutions not existing, implying that some vectors are not part of the column spaces, and these spaces I keep talking about are vector spaces. So I will have to start from there, and that's when I will basically discuss that these other rows, these non-pivotal columns can be expressed as some linear combination of the pivotal ones. Because for example, this second non-pivotal column 2 0 0 0 can be expressed as 2 times the first pivotal column, and 2 1 0 0, the fourth one, can be expressed as 2 times the first pivotal column plus I believe the third pivotal column, 1 times the third pivotal column. And this idea of basically expressing any vector like this in terms of some linear combination of two more fundamental vectors means that these two vectors are linearly dependent on the others in the system. It basically not giving any new information. They basically just, if say x1's here, x3 is here, this guy is somewhere in between. It's in the span. And all these words are gonna come up soon, so don't worry about that. I'm gonna make a video next on this. And whenever you want to check whether vectors are linearly dependent or independent, you just put them in a regular matrix. Don't worry about augmented matrix, because then we're not solving any system of equations. And then just row reduce them into RREF, and then see which columns become pivotal columns. The ones that become pivotal columns are the fundamental ones, are the ones that you can express the free columns in terms of. And then this linear dependence basically gives us the idea of a null space. We're going to talk about this later, so stay tuned for that. It's very important. I hope you enjoyed this video though. And just to add, this basic idea of writing this degrees of freedom in this case are more than the conditions, so there's higher chances for a system of equations like this to basically just blow up, like take many possible values, giving us infinite number of solutions, because there's just too much freedom. There's not many constraints, and there's just a surplus of information or data and stuff like that. So stuff like this is bound to happen. Please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Diagram in the math community. Stay tuned for the next video, which is going to be way more interesting and way more fundamental the way I think about it. And in the meantime, peace out.